Today we're going to do section 6.6. First, let's look at book. This page was already scanned last time, but I will briefly do it again. And being that most of the page will be looking over most of the page, okay, the top and the bottom. Why is the top so bent looking? Who knows? Anyway, so that's that. All right, next, page 200 and 201. We have that, I guess. Okay, and then zoom in a little bit more on top. And a bit on the bottom. Let's see, am I not zooming in enough? Okay, let's see what I'm doing on top. That's good enough. Okay, finally, that is this stuff. Okay, I think my lighting is a little bit weird. I will do something about that. Let's see, it's parallel. Let's be parallel. Okay. And, all right, so that should do it. So let's start in sections chapter 6.6, where we have on page 198. So please read the little introductory paragraph yourself here, and then and we're going to look at the Duhamel's theorem. Now this Duhamel's theorem is an improvement or advancement of the previous Duhamel's theorem we looked at before. And so let's look at the previous one first to see what we're talking about. The previous theorem that we looked at many times just says that if you have two functions, okay, and with all the proper requirements, then the integral of the two functions is the same, is defined by the limit of the sum of each function times whatever it needs to multiply. Okay, that's all Duhamel's theorem says. Because normally the integration is defined for just one function, right? But if you have two, it still works with a different eta at k. That's the main catch. Okay, it don't have to be the same, and as long as all the conditions satisfy, it still works. Now the new Duhamel's function is the theorem is the same thing. I mean a similar idea, except that now before we had f of x and g of x. Now we have f of xy, g of xy. So one more dimension, but otherwise the story sounds is almost identical. Basically, yeah, you see, the integral over r of function f times function g is the sum of f and g. Each one has well, it's similar anyway. The f is have xk, yk, and g has eta sine eta. All right, so that should be the same kind of deal. Well, anyway, a similar kind of deal anyway. So that's the Duhamel's theorem. The proof is to be omitted by the book, so we'll also ignore it. However, bear in mind that it depends on the uniform continuity of a continuous function in a closed region, closed and bounded region. Okay, you can have a closed and unbounded region, and that would not be good. And because the word closed region just means it has all the boundary points. So any region that you might wonder, what is a closed unbounded region? For example, the region, I just quickly tell you that the region, okay, that's bigger than the unit circle, including the unit circle, is a closed unbounded region. It extends to infinity. It contains all its boundary points. Okay, so and well, yeah, it has no boundary on the outside, so by definition this thing is a closed and bounded region, even though, I mean, a closed unbounded region, You know, so infinite regions can still be closed. Anyway, so let's look at section 6.2. So next, let's look at the section 6.2, center of gravity. We have the definition of center of gravity as given is equal to the sum of the distance times mass. Okay, in this section, we're not going to care about the mass that much. We mostly just pay attention to the area, because the mass is equal to the area times the density, but we always pretend that the density is 1, basically. So so we don't care about the so then the mass is most of the time just the area. But anyway, when you sum, you might remember this from physics, or just look at this. Okay, the center of gravity is defined this way for discrete particles as well as for continuous sheets. So continuous sheets, then of course, then you turn into a limiting, let's see, where is it? Over here. A limiting integral situation, but it's the same concept. X bar is this, Y bar is this, and the mass, which is the area, is the integral of F ds. F is the density function. Like I said, if F is 1, then the density then the M just becomes the same as A. And so please read this part yourself. Okay, it's a description of, this is basically a repeat of what we had earlier. I believe we did something like this in, what, 1D or something? I don't know. But anyway, it's the same principle. And so please read this part yourself, okay? And it's mostly a physical description of something I believe we already have focused on. And then this page, and then the following page does the same thing. The ones over here. Once you get you just have to pay attention to this formula right here. That's all I noticed. And please do example A yourself. Okay, find the center of gravity of triangular region. I'm sure you've done this in the past, but yeah, let's do this again. If you just follow, like I said, follow this formula, and then everything falls out right away, and not much to it. But please read all this yourself. Just make sure that you don't miss anything. And then we'll move on to section subsection 6.3, moments of inertia. With the moment of inertia is the same idea. Moments of inertia is the distance times the function. That is, you have an that is, see here, x, you have x squared and y squared. In other words, r squared, okay, times fxy dx. So then, so g is the square of the distance from the point xy to the line in the plane, and so on. So the I is defined this way, okay? And anyway, so please read that yourself as well, and also do example B on the next page. Again, it's a very simple, straightforward calculation of applying something. And so please do that yourself. And with that, we've come to the end of this section. It's a short section. Well, these applications usually are short because there's not much to it. You just integrate. I mean, what do you want, right? So for homework, please do. Let's see, where is the homework page? Where is the homework? Homework is on page 201. Okay, page 201 right here. I got it. Let me write it down first. So for homework, please do, let's see, problems 2, 3, 10, 11, 13, 16, and 17. And that should do it. All right, and when you're done, let's talk about them. Okay, I forgot to show you a picture I drew for example A on page, whatever page this is. Example A on page 9, right. This example describes some kind of a triangular region, okay, and that is the region is drawn like this. In case, being that I drew the picture, I might as well show it to you. So the any triangle can be lined up to look like this. Okay, it doesn't matter what shape the triangle is in. So anyway, I forgot to show you that. I don't know if it matters. And then next, let's look at problem 2. Problem 2 says that, what does problem 2 say? The center of gravity of some area bounded by that curve. What is that curve? That curve is, let's see, find it. Okay, actually, we don't even care what the curve is. Okay, we know the curve is symmetrical. And because of all the squares and x and y look the same, okay, they both raised to the power 2n. So with that information, you can plot it out, and it looks something like a circle that's being blown up to fit into the square. Or we can just do this, that then y equals the plus or minus square root of 1 minus x 2n. And so let's integrate. X bar, by definition, okay, is equal to that thing. So we plug everything in and crank it out. So what? Now this integration, we don't even have to do it because this is an odd function. And being that this is even on the inside, and then there's an x here, so make it odd. And all odd functions integrating symmetrically from -1 to 1 is automatically 0. And so x bar is 0, and similarly y bar is also 0, and that's the answer to problem 2. So next, let's look at problem 3, where's problem 3? Okay, so next let's look at problem 3, which is we're trying to find the moment of inertia of some disk that has a radial density. Okay, and so to do that, we will simply plug everything in like it says. Okay, so let's plug it in, and once we plug this thing in, then we get, yeah, see, we get the answer immediately without trouble. So that's that. That's for problem 3. So next, let's consider problem 10. We need a formula for the moment of inertia of a solid of revolution about the axis of revolution. All right, so that, well, that's just a matter of plugging stuff in. Okay, I mean, we have a graph of something, right? And then we'll spin this thing around. And we haven't really done the volume, but we'll just apply the same principle. And yeah, so we'll do the integration of each one, okay, each slice, and then sum it up from A to B is what I did here. And then so then the volume of what are we doing? Oh, yeah, the moment of inertia. The volume itself is calculated like this, okay? And then so the inertia, then the thing, we'll use the polar coordinates and do the integration. And very soon I get this formula. And now this formula is proven. Then I tested it by checking it with a cone, a standard cone. I calculated the moment of inertia with my formula, and then double checked it with the standard cone's moment of inertia. It checks out. I also checked it with a sphere, and it's also check out. Where I'm doing all these checking because we don't have the answer to problem 10, I don't think. So then I wanted to double check to make sure that the answer I got is indeed correct. And after I did that, then it dawned on me that maybe I can just Google it, right? And Google says that my answer is indeed correct. See, here's what Google says. Oops. The AI says that the moment of inertia rho is just the density, so we don't care. And it's pi over 2 y to the power 4 dx, which is what I have right here. See, I have it written down right here. Pi over 2, the function to the power 4th dx, and integrating from A to B. So that should be good. And then next, let's do problem 11, which is we need to find the moment of inertia for the torus about its axis. So we're spinning the right way. And so to find the moment of inertia for the torus, we use the formula that we just arrived from problem 10, right? So we'll do being the torus has a top half and a bottom half of the circle, we will have, we'll do the top half, the moment of inertia, we'll do the top half and then subtract it by the bottom half. Which sounds fine, and then the formula of the circle up there goes by this. Where is it? Right here. Okay, that's the formula of the circle up there. Big R is the distance from origin to the middle of the circle. And remember, this circle is being spun around the x-axis to create the torus. And so well, anyway, so imagine this thing going all the way around. But anyway, so that is the formula of just the circle, okay? And then we have H1 and H2, which is fine, but and then I did the subtraction here by the calculator because we have to raise it to the 4th power, and I wasn't going to do that. But anyway, and maybe it's not as hard as it looks. I think it looks hard. Either way, I didn't do it. So I put this into the calculator, which calculated this thing, and then when I try to put that into the calculator to do the integration, the Wolfram calculator couldn't do it. Okay, it just is too hard, which forced me to do this by hand. Okay, and how are we doing this by hand? So I did this after some futile attempt to try to get the Wolfram calculator to work and failed. So finally I was forced to do this by hand, and doing it by hand we got to this part well, I guess I was forced to let x equal to r sine theta, which I seriously didn't want to bother, but there was no getting out of it. So, but once I did that, however, it didn't take very much to see. I quickly got to here where the formula looks much better. Okay, so now we have a formula which we have a bunch of cosines with constants in there, right? And integrating only from 0 to pi over 2. Then, because we have a square root situation, but luckily everything is symmetrical on the minus and plus side. So then I can integrate only from 0 to pi over 2, and then not worry about who's doing what. What the square root might do to me. And so I typed that into the calculator, and now there's after not that much steps, actually, not that many steps, and the calculator now, Wolfram was able to crank this out, okay, and told me is this, which ended up being the right answer, because at this point I just Googled the volume of the torus, which is this formula right here. And the volume is much easier to calculate, being that it's just x squared, but I wasn't going to do that. And being the book didn't give the volume either, right? The book answer just says m. So m, which is v, because our density is 1. So then this is the right answer. And the calculator was able to do this very nicely. And I will show it to you here, even though this is not a big deal. But I was very happy that I was finally able to get the calculator to work. Okay, so once I typed this in, it was able to give me this thing immediately. Whereas the other, and I only went through a couple of steps to get to here. Whereas the other formula, the calculator simply says, "I don't know what to do. I have no idea what you're talking about," or something. So this is the formula I originally typed into the Wolfram calculator. It couldn't do it, but once I did a simple substitution and we got to this point, then it could do it just fine. Okay, I put A as small r and B as big R, which is what the book does too. And the book's answer is looking like that. All right, that's problem 11. Okay, so next let's look at problem 13. I'm not sure why the book even assigned problem 13, but it looks funny, so I did it. We have, the guy is in a dome-shaped building, okay, and he can stand up when the average height of a dome-shaped building will be volume divided by base area, which happens to be two-thirds of the radius, okay? And then we use the Pythagoras theorem and figure out how far out the guy can stand, which is r square root 5 over 9. That's the right answer. That's all I have to say about that. That's problem 13. Next, problem 16, we have some old-sounding thing here, okay? To what is it called? Papa or something? Where's Papa? Let me turn the page. Pappus, okay? The theorem of Pappus, which says that the volume of revolution its volume is going to be equal to 2 pi times the, what is that? The area that we start with, and then times y bar, that is some centroid. The y bar is defined on page, on the previous page, 200. Okay, so I did that. It says what it wants. So we plugged everything. I plugged everything in like this, and then y bar equals to that thing, and as a result, then being that v is this thing, okay, that these two conditions prove that v equals to y bar a, and that's problem 16. Next, let's look at problem 17, which is now we're gonna find the volume of this stuff. What stuff is that? It's the intersection of a sphere and then a cone, which calls for the Desmos 3D, which I did. Okay, I plotted these things into Desmos 3D, and here's the cone. Okay, and then the sphere. There's only a little bit of the sphere, so we're gonna calculate the volume of this thing based on that formula. What was the formula again? Well, whatever the formula is, we're going to base on it, okay? But anyway, that is, so the formula has something to do with the area of this thing. That is, this thing that we're spinning this thing around to create that. So the formula says we'll calculate the area of this thing, and then the x bar or y bar or something, and then multiply those things together with 2 pi, etc. So that's what I did. And let's see. So when we do that, we still have to figure out what x bar is. So the volume is that thing, and by the time we get everything done, the volume will be equal to the two parts. Okay, that is this is the sphere part. No, let's not look at this line. This line is too messed up. I think I rewrote it here. Maybe I should scratch that out. All right, so I scratched that out. Following this formula, I plug things in, except that we have two parts. There's the cone, and that is the sphere. And we're integrating in the y direction, because that's just how I drew it. And so as a result, the limits, okay, I knew that it might turn out to be negative, so I slapped the absolute value here. Because it depends on which way you integrate, from top to bottom or bottom to top or something. And so anyway, I stuck the absolute value here, which was good because these things turn out to be negative. But they're both negative, so because I was doing it consistently, so see, from a to that number and from this number to minus a, okay? So they are the same sign, so when they added up, it became this. After I plug this thing into the calculator, it becomes this, which is the right answer. And let me show you what the Wolfram calculator says. See, here is the graph again, and let me move it over. Here's what the calculator says. See, I typed in both integrals, and well, separately at first. I want to make sure that they're not one positive and one negative, because but they end up being both negative. So then I put them in the same formula. See, that calculator can do two integrals added together if you want. So, and then the result is exactly what the book says, except there's a negative sign, which we will ignore. Yeah, I could have changed these limits, make them go the other way, but that's too much work to retype it, so I didn't bother. So the result calculated to be negative, and we'll just throw away the negative sign, and that gives us the right answer. So that should be the end of this section.